Hello viewers, welcome to Adisha Tech Tutorial. So in this video we will be discussing the first module of basic electronics engineering subject, that is the semiconductor. So let's begin. So this module we will be studying it in three parts. So the first part will consist of the types of semiconductor. First will be your intrinsic, second one is the extrinsic, which is also called as doped semiconductor. Your part 2 will consist of the types of current flow in semiconductors, the drift current and the diffusion current. Your part 3 will consist of the PN junction. Now what is PN junction? P is the p-type semiconductor, N is the n-type semiconductor, and they both combine and form a junction known as PN junction. So in this part we will study what happens to the PN junction when there is no voltage given to the PN junction and when there is some applied voltage. Lastly, in this part 3 we will study the capacitive effect in between the PN junction. So let's begin with the part 1. So as I said you, there are two types of semiconductor, intrinsic and extrinsic. Extrinsic is further divided into two types, that is P type and N type. Next is the doping. It is a process by which we can vary the conductivity of a semiconductor. Next is the types of charge carrier inside the semiconductor, which is electrons and holes. So let's begin with the intrinsic semiconductor. So here we are taking silicon material as a semiconductor material as a silicon atom whose atomic number is 14. So according to the atomic structure model, we are having a nucleus and electrons orbiting around the nucleus on a certain energy level. So for silicon atom, the first energy level will consist of 2 electrons, second will consist of 8 electrons, and the third energy level will consist of 4 electrons. But in order for the atom to become stable, how much it requires? 8. So let's see how it is gaining its 8 electron with the help of a structure. So this structure which you can see is known as tetrahedral structure of a silicon crystal, or it is also said as a diamond structure. So these blue circles are nothing but silicon atoms. So to attain 8 valence electrons in its third orbit, what it requires? It requires more 4 electrons. So it sets its 4 valence electrons with the 4 other silicon atoms with the help of covalent bonds and become stable and by forming a tetrahedral structure. It is this is a three-dimensional view. It is much clearer in two-dimensional view. So here you can see this silicon atom shares its 4, these dots are electrons, its 4 electrons with the 4 silicon atoms in order to gain 8 electrons with the help of covalent bonds and become stable. So whenever this structure or tetrahedral structure repeats itself in a periodic manner, it forms a structure known as lattice structures. Now let's move on to what happens when there is some thermal energy given to the intrinsic semiconductor. So here you can see a figure. This figure is called, as we have discussed, this is called the bond model, and this figure is called the band model. So what is difference between a bond and a band? We are not dealing here with a isolated silicon atom. We are dealing with multiple silicon atoms. So each silicon atom's energy level will have a slightly difference in energy. So the combination of these energy levels of silicon atoms give rise to a band, not a single energy level. We will get a band structure. So this is a band structure of the silicon crystal. So now we will see what happens when there is no temperature. Let's see. Let us assume the 0 Kelvin temperature. So at 0 Kelvin temperature, silicon crystal will not conduct and behaves as an insulator. Why? Because the electrons are present inside the band known as valence band, and no electrons are present in the higher band, that is the conduction band which help in the conduction process. So there is no conduction and there is a gap which the electrons require. There is a forbidden energy gap which the electrons require to move from valence to the conduction band. So that energy is not attainable at 0 Kelvin. So your silicon crystal behaves as an insulator. And this forbidden energy gap can be measured with the help of electron volt, and for silicon atom, silicon crystal, it is 1.1 electron volt. Okay, so it is behaving as an insulator as there is no electrons present inside the conduction band. Now what happens when we increase the temperature? Let's say the room temperature, which is approximately equal to 300 Kelvin. So at 300 Kelvin, your electrons gain this thermal energy and moves to the overcomes the forbidden energy gap and moves towards the conduction band and becomes conduction electrons, or we can say it as the free electrons. So after leaving the valence band, these electrons uh, leaves a void space inside the valence band, that is called the hole. So it can also be explained with the bond diagram. So whenever temperature increases, your covalent bond is broken and electron moves out of the covalent bond, leaving behind a hole and becoming a free electron. So here you can see two a free electron and a hole is generated, or we can say it as an electron hole pair is generated. Electron hole pairs is generated when we give thermal energy to an intrinsic semiconductor. Now let's see the very important relationship, which is N into P is equal to Ni square. So here your N is the concentration of free electrons. What is concentration? It is the number of electrons per unit volume. We measure the number of electrons and holes in terms of unit volume because we are dealing with a three-dimensional structure of a silicon crystal. So that number of electrons per unit volume is nothing but it is said as the concentration. So the concentration of free electrons is represented by small n and the concentration of holes is represented by P. So here you can see in this figure that the number of electrons in the conduction band is equal to the number of holes generated in the valence band. So the N is equal to P, which is nothing but is equal to an intrinsic carrier concentration, which is equal to Ni. So what is Ni? Ni is the number of electrons or holes in intrinsic semiconductor per unit volume. So when we multiply N and P, we get Ni square. So with the help of semiconductor physics, our Ni can be calculated as 1.5 into 10 to the power 10 per centimeter cube. So this is a very important relation which will also be used in case of extrinsic semiconductor. Now in the last section of intrinsic semiconductor, let's see what happens. So when sufficient number of electrons moves from valence band to the conduction band, the electrons inside the conduction band moves randomly inside the silicon crystal, and as a result what happens, these electrons start recombining with the holes present inside the silicon crystal. So this is called the thermal generation or GTH, and this is called the recombination RTH. So whenever your GTH becomes equal to RTH, the electron hole pair or EHP disappear, which results in a less amount of conduction or charge carriers inside the semiconductor, and the intrinsic semiconductor doesn't conduct. And this stage, when generation rate is equal to recombination rate, is called the thermal equilibrium. So for this purpose, as the intrinsic semiconductor is not conducting, we are moving towards the extrinsic semiconductor. Now one important process that is called doping, or it is also called addition of impurity atoms, is done to the semiconductor. So what is doping? As I said you, it changes the conducting property, or here we can use it changes the carrier concentration. It changes the number of holes. Changing the carrier concentration means changing the number of holes, that is N or P, inside the semiconductor per unit volume. Okay. So now let's see how we are attaining this N-type semiconductor and P-type semiconductor. In order to get an N-type semiconductor, we have to increase the number of free electrons inside the semiconductor. So to increase the concentration of free electrons, what we will do, we have to add a pentavalent impurity atom. What do you mean by pentavalent atom? Pentavalent atom are those atoms having valency of 5. So here the examples of pentavalent atoms are phosphorus, represented as P, antimony Sb, arsenic As, and these atoms are called the donor atoms. Why they are called donor atoms? Because your silicon atom requires 4 electrons to become stable, 4 more electrons to become stable, but what we are giving here, we are giving 5 electrons. So 4 of the 5 electrons combine to make the covalent bond, and one of the electrons is left free. So the number of electrons, free electrons, or the concentration of free electrons inside the semiconductor, inside the N-type semiconductor, increases. So they are called the donor atoms. Next, moving on to the P-type semiconductor. So to get the P-type semiconductor, we have to add trivalent impurity. So trivalent impurity is the atom having the valency of 3, whose examples are boron, B, gallium, Ga, indium, In. These are called the acceptor atoms. So again same thing. So here silicon atoms require 4, but trivalent gives 3, and one of the covalent bond is not completed. It requires one more. So they are called the acceptor atoms. One more electron they require. So they have to accept one more electron. So they are known as the acceptor atoms. So pentavalent atoms or impurities are called the donor atoms, and trivalent impurities are called the acceptor atoms. Sometimes in competitive examination questions are asked about this pentavalent and trivalent. So just remember the examples. So N-type semiconductor, let's discuss detailing. So as I said you, in N-type semiconductor, the number of pentavalent impurities are more. So here the concentration of pentavalent impurity or donor atoms is represented by Nd. So now we can say that the concentration of free electrons. So N subscript N is for this subscript N, which is written here, is for N-type semiconductor. Pn is the concentration of holes inside N-type, and Nn is the concentration of electrons inside N-type. So here your free electrons, which is present in N-type, is nothing but it is equal to the concentration of the donor atoms. So Nn is equal to Nd. Now, as discussed earlier in intrinsic semiconductor, your intrinsic carrier concentration Ni is equal to N is equal to P. But here N is greater than P because of the pentavalent impurities. So N is greater than P, that means N is also greater than Ni. It is much greater than Ni. So here as N is greater than Ni, so Nd also becomes greater than Ni. So this is an important relation which we are using. So you got to remember that in N-type semiconductor, your Nd, or the concentration of donor atoms, is greater than your intrinsic carrier concentration, that is Ni. So now we got to find out a relationship between your concentration of holes and free electrons inside N-type semiconductor. So in order to get a relationship, we have to use the same formula, that is N into P is equal to Ni square. This is same This formula is same for intrinsic and extrinsic, which can be explained with the help of mass action law. So its proof can be done if required. Okay. With the help of mass action law, we can prove that Np is equal to Ni square for extrinsic semiconductor also. So by using this formula, we can substitute here your Nn as Nd, and we can get we get an equation for Pn, that is the concentration of holes inside the n-type semiconductor, which is nothing but it is equal to Ni square divided by Nd, which is concentration of donor atoms. Lastly, in the last part, we will be studying in this video the p-type semiconductor. So same as n-type semiconductor, here the concentration of holes is more as we are adding trivalent impurity. So here the concentration of trivalent impurity or acceptor atom is written as Na. So here we can write the concentration of holes is nothing but they are equal to concentration of acceptor atom, which is equal to Na. Now in the same manner, your Na as P is greater than Ni according to the formula, Ni is equal to P is equal to N. So as number of holes is more here, so your P is more than Ni. So your Na acceptor atom concentration is also more than Ni. Next, we can also find a simple relationship as previous one. So we will use that same formula, Np is equal to Ni square, and by substituting P is equal to Na, we can get a relationship for concentration of electrons, that is Np is equal to Ni square divided by Na. Here one important uh, view is about your band diagram. So here you can see in this band diagram, you are having a valence band and a conduction band and one extra energy level, that is called the acceptor level or acceptor energy level, or represented as Ea, and it is nearer to the valence band because it is devoid of electrons. It is having only holes. Similarly, in this bond diagram, you can see that we are having a void space inside the covalent bond, that is we are having only 3 covalent bond and 1 covalent bond is left, and it requires electrons, one more electrons, that is called the acceptor atom, in order to complete its covalent bond. So this is all about your acceptor impurity. Similarly, in this n type also we can see that figure. In this band diagram we can see we are having an extra energy level which is nearer to the conduction band. This is called the donor energy level, Ed. So these are having extra electrons, and these electrons energy level is present near to the conduction band. So this you got to remember that the donor energy level is present near to the conduction band and acceptor energy level is present near to the valence band. And in this n type you can see we are having a free electron. We are having 4 covalent bonds. Here phosphorus is taken as a pentavalent impurity and we are having 4 covalent bonds and one of the free electrons is left behind. So the number of free electrons inside this n type is much more than the number of holes generated because of thermal energy. So this is all about your first part of semiconductor. In the third video of my uh, tutorial, we will be discussing the problems associated with this part 1. So stay tuned for my next video. Take care. Goodbye.